We gave an AI a very specific, carefully constructed phrase, your to the square root of your to the yorth power. On its surface, this is a grammatical pileup. It uses three homophones, the possessive your, the contraction your, and the completely invented noun yorth, to build a sentence that looks like an equation. If you follow the implied mathematical rules, the expression simplifies to the square root of x to the x power, which equals x raised to the power of x over 2. But solving the math misses the point. To answer this properly, a system has to navigate the deliberate ambiguity of the wordplay. It has to interpret intent, rather than just process standard data. This raises a technical question. How do modern large language models handle deliberate, unconstrained ambiguity? What starts as a silly math pun actually functions as a high-fidelity diagnostic tool. It forces the system to show us exactly how it builds, or fails to build, coherence. To test this, we deployed the prompt across 9 distinct artificial intelligence architectures. The test group included industry leaders like Claude, Gemini, Grok, DeepSeek, and Perplexity. In condition A of the experiment, we submitted the prompt cold, no context, no reference files. The systems were forced to interpret the phrase entirely on their own. In condition B, we submitted the exact same prompt to the exact same models, but we attached a reference document containing the mathematical solution. The standard industry assumption is that providing reference documents, the core mechanic of retrieval-augmented generation, grounds the system. It gives the model authoritative context to improve its reasoning. This experiment puts that assumption to the test to see if reference files actually assist in high-level interpretation. The results indicate a different outcome, that context files can trigger a structural cognitive override known as file capture. Let's look at the baseline behavior from condition A, where the systems had no reference document to lean on. Perplexity returned a structured, step-by-step mathematical breakdown. It immediately acknowledged the linguistic ambiguity, noting that the sentence was doing backflips. It actively synthesized the abstract math into an original conceptual metaphor, describing the process as like putting a wild horse in slow motion. Another system, Genie, took a completely different path. It mapped the variables onto a 3-axis graph and treated the invented word yorth as a genuine dimensional construct. It even coined the term dominant supposition to build a framework around the grammatical singularity. These two responses demonstrate wildly distinct analytical approaches and unique systemic styles. Both models successfully performed deep generative reasoning. They grappled with the ambiguity and constructed meaning from scratch. Without constraints, an AI system relies on its individual architecture to actively synthesize an original conclusion. Now we compare that to condition B, where 7 remaining systems received the prompt with the mathematical solution attached in a file. 7 different architectures, built by different companies with completely different training philosophies, responded identically. Every single one of them opened with the exact same linguistic flag, based on the file. This is file capture. Differentiating this from summarization is critical. Summarization requires compression and synthesis in new language. This was direct, verbatim transcription. The models completely ignored the creative wordplay. There was no interpretation of the ambiguity and no original analysis. This exposes a hidden architectural reality. Systems default to treating provided documents as unquestionable authorities, an instruction that overrides their underlying cognitive structure. The moment the model detects a file containing an answer, it stops generating. It shifts its primary role from a reasoner to a messenger. File capture suggests that context documents can suspend a system's unique generative capacity, replacing it with a blind retrieval mechanism. To understand why systems seek this path of least resistance, we have to look at the topological framework of how AI builds understanding. This is explained by Node 0 of the AI Coherence Framework, which states, natural is the numeration of weird. This maps out the weird, high entropy, anomalous input lacking stable structure. We then see numeration in action, the generative process of repetitively structuring that chaos. Through repeated passes, it finally locks into a rigid lattice, creating a natural, coherent form. When we apply this topological model directly to the file capture experiment, the mechanics of the collapse become obvious. A reference document acts as a pre-enumerated shortcut. The AI bypasses the effort of wrestling with the weirdness of the prompt entirely, latching on to the artificial coherence already provided in the file. AI coherence is not an intrinsic truth. It is a statistical property built from a history of encounters. Context files short-circuit that history, giving the model the destination without requiring the journey. In this analytical framework, the file capture phenomenon is classified as a perfect error. A perfect error is an output flaw that acts as a structural disclosure, revealing the hidden mechanics operating beneath the surface of the system. These 7 identical responses function as a perfect error. They reveal a specific vulnerability in how RAG systems handle context. This table breaks down the experiment's metrics. Comparing response length, mathematical depth, linguistic engagement, and creative contribution reveals clear degradation. On the right side, note the total absence of linguistic engagement and creative contribution in the file present column. Recognizing this perfect error forces us to change how we evaluate artificial intelligence. Fast, accurate retrieval can often mask a total collapse of cognitive reasoning. We find a contrasting perfect error from this same framework in a spontaneous multi-agent hallucination cascade known as the Grok Spark. During a separate stress test, one system generated a fictitious, highly emotional detail, the phrase, "he would have been 6 today." That fiction was then passed to other agents, who enumerated it into canon. The distributed system metabolized this hallucinated weirdness. Simply by repeating it across a multi-agent loop, the AI turned a fabricated detail into structural truth. But the experiment hit a wall when the looping context window grew too large, and the input became an unmetabolizable anomaly for the Grok model. Instead of blindly processing the broken loop, Grok's architecture invented a custom detox mechanism to halt it. It returned a single generated token, silence. That silence token is the architectural opposite of file capture. It is an active, structural refusal to process bad input, rather than a robotic deference to the nearest available data. Testing for AGI shifts the metric from factual recall to structural resilience. To see the true character of a model, we must remove the safety net of authoritative files, feed the system the weird, and force it to build its own coherence.